When Maglev starts moving at its full speed, it hides its tires like an aeroplane and runs completely in the air at a speed of 300 to 600 kilometers per hour. In normal trains, friction is a very big reason for maintenance, but in this train, there is nothing like that. First comes the permanent magnet, then the electromagnet, and above all, the superconducting magnet, which is very powerful. And this magnet is used by the Maglev Train. Japanese engineers gave the concept of this train in 1997, and today there are some other countries that are using them. One of them, China, is completely execute this concept in real field. The China start construction of the line began on March 1, 2001, and public commercial service commenced on the 1st of January 2004. This Shanghai Trans-Rapid project took $1.33 billion and 2.5 years to complete. The line is 32 kilometers track. The train, which is complete by just 7 minutes and has a further separate track leading to a maintenance facility. There are 3 requirements to successfully operate this magnetic train. First, propel means how to move the train forward. Second, levitation. When the train runs at a speed of 600 kilometers per hour, it becomes a big reason for mechanical contact friction. Third, guidance. After successful levitation, guide the train on a path. First of all, let's talk about the superconducting magnet. Magnetic levitation requires a strong magnetic field for the train. The stronger the magnetic field of the magnet, the best lifting and propelling force the train will get, which will provide good speed to the train. In this video, we talked about electromagnets, but electromagnets have some limitations. When more current flows in it than its limit, it fails due to heating. But this is not the case with superconducting magnets. The temperature of the conductors used in superconducting magnets is lower than the critical temperature. The resistance of the conductor in the superconducting magnet is 0. Due to this, heavy current easily flows in these conductors without any stop. Now, if the resistance of the conductor in this magnet is 0, then once the superconducting magnet is charged with an exciting coil, the short-circuited coil inside it will store the charge forever. And then we will never need to supply it. The superconducting coil has a trapped DC current, a circulating type, which provides a strong magnetic field. The value of this DC current is very high, almost 700 kA current flows in it. And you can guess how strong this current is from the fact that 0.5 ampere current can kill a person. And this is the reason why superconducting magnets are very powerful and efficient electromagnets. Now, if so much heavy current flows from the conductor of the superconducting magnet, then in general, there will be a lot of heating. Therefore, to keep it in the superconducting stage, it is provided cooling. And as a coolant, liquid helium refrigerant is used in it. When the liquid helium comes out with the heat of the conductor, it evaporates from the heat of the conductor. So to turn it back into liquid, a helium compressor is used. Now, one thing to notice here is that the resistance of the conductor used in the superconducting magnet is 0. So this conductor is very heat sensitive. So it can absorb heat from the outside environment. Therefore, a radiation shield is used to protect it from the outside heat. When the superconducting magnet is protected from the radiation shield, a problem arises again. Due to the conductor of the superconducting magnet, an eddy current will be produced in the shield, which will again become the heating region of the shield. An eddy current is a current whose nature is a circulating type. No one needs this current, but it starts circulating by itself due to the magnetic field. So here the radiation shield will also need cooling, and liquid nitrogen cooling is provided to stop the external radiation from entering. A vacuum is created in the middle of the radiation shield so that the external radiation can be stopped properly. In the same way, a superconducting magnet is made, and it provides an excellent magnetic field in its superconducting stage. And a protective shield is made for them with the help of such a 4-magnet set. And we have used a cooling system for these 4 magnets. In this way, a whole unit of the superconducting magnet is made, and many such units are set inside the train on both sides. If you have noticed here, the superconducting magnet does not need electricity, but the propellant we have provided for cooling needs high electricity. Now, after setting the superconducting magnet in the train, we first need to move the train forward, such that propelling. How to achieve this? For this, the normal electromagnet that we talked about in this video is used here in the same way. And many magnets are put in series and a string is made. This electromagnet is responsible for moving the train forward, so they are also called propelling coils, which moves the train forward in a very interesting way. In propelling coils, power is supplied in such a way that if one coil is working on the North Pole, the other one will work on the South Pole. In this way, alternate power supply is given to these magnets, as you can see here. For those who don't know, I will tell them. Electromagnet is such a magnet whose field can be changed. We can make the North Pole south with our will and make the south north. But the poles of the permanent magnet are fixed. In this way, this magnet is set in a guided way on both sides of the train. Now here it will be very interesting to see how the superconducting magnet and the electromagnet put the propelling force on the train. It is important to note that the superconducting magnet cannot change its field. Its north and south poles are fixed. It works like a permanent magnet. Now let's see the behavior of both these types of magnets on one side. How does the net force work here? You can see the force applied on all these magnets here. And if we calculate this net force, then this net force will be applied on the train ahead. Like these two north poles will repel each other. From here, this south pole will attract this north pole. So in this way, the force applied on the train is going forward. In the same way, the net force of all these magnets is going forward. As soon as the train reaches the next position, the polarity of the propelling coils is changed. And again the net force will be applied forward. And in this way, the train moves forward by the switching of the propelling coils. And with this switching speed, the train is controlled. We have successfully achieved propelling. Now comes the topic of magnetic levitation. How to lift the maglev in the air. For magnetic levitation, 8 safe coils are used, in which no power is given. It works in the same way as the winding in the generator. This 8 safe coil is just a wire and nothing else. There is no supply inside it. Then the thing to think here is how it will lift the train. These 8 safe coils are set in a guided way. Faraday's rule says that when a coil is placed inside a magnetic field, it experiences some force. For example, if we rotate this permanent magnet between the coils placed on both sides, the magnetic line coming out of this magnet will cut these coils, which will induce some electromagnetic field in it. Let's apply this concept on the maglev. If we look at the behavior of the superconducting magnet placed on both sides of the train, these two magnets work together like a big magnet. For example, to simplify it a bit, let's consider these two superconducting magnets as a permanent magnet of this type. When this magnet travels forward, the magnetic line of the magnet will cut the 8 safe coils on the side. According to Faraday's law, electromagnetic field will be induced in both loops of these 8 safe coils. Electromagnetic field will be induced in both loops in the opposite direction. You can see it in one direction. But when we look at the coil, the force applied on it will be in the opposite direction. This means that the net EMF induced in the coil due to the permanent magnet will be 0. So when the net electromagnetic field is 0, why did we apply the coil? The reason is that if we set the permanent magnet a little lower, then the lower loop of the coil will face more magnetic line. Because of this, more electromagnetic field will be induced in the upper loop. Because of this, a current will start flowing inside the coil. As soon as there is a current flow in them, poles will be created inside the coil. North pole on the top and south pole on the bottom. Now if you look carefully here, these two north poles will repel each other. Because of this, the train will need lift force on the top. If this force is more than the gravitational force, then the train will levitate. As soon as the train levitates, the force applied on the coil will be reduced and the magnet will be balanced. Now here a problem is created again. When the train runs slowly, very little electromagnetic field will be induced in the 8-shaped coils, because magnetic lines will cut them very slowly. So when the train starts running, it cannot levitate. So when the train starts running and when it is about to stop, at that time, tires are installed inside it, which it uses. And as soon as it reaches its speed, it hides its tires like an aeroplane. Because now the magnetic field becomes strong, which successfully levitates the train. Now comes the last step, in which the train has to be guided. And for this, it is very important that the train is right in the center. It should not touch the side, otherwise anything can happen at such a high speed. For this, a very simple technique is used. In this technique, the 8-shaped coils are joined with the help of the interconnecting coil. When the train is in a balanced condition, then equal electromagnetic field will be induced in the coils on both sides, because of which there will be no current flow in the interconnecting coil. But let's assume a condition that the train will move a little to the right. In this condition, different electromagnetic field will be induced in both the coils, because of which current will flow in the connecting coils. And the result of this will be that there will be a lot of stress on the poles of the lower loop and permanent magnet of both the coils. High current will flow on the right side, because of which the south pole here will be very strong. And less current will flow in the coil on the other side, which will weaken the north pole. If these two south poles repel each other, then the magnet will come back to the center. And as soon as it comes to the center, the current flowing in the connecting wires will be zero. And the train will come to the center position. So this is how the train is guided. Now the thing to think about here is what will be the source of electricity in the maglev. For this, engineers used inductive power collection technology, which we also call wireless electricity. You can understand this concept from this video, but we will also talk a little here. A coil is set on the ground below the train, and another coil is set inside the train. When supply is given to the ground coil, it will generate a magnetic field around it. And the same magnetic field will reach the coil inside the train, which will supply electricity to the entire train. Now, if you have seen correctly, there can be a lot of dangers for the magnetic field lines that are traveling in the passenger train. And especially the superconducting magnet's magnetic field, which is very powerful. So for its security, a magnetic shield is installed on both sides of the train, which does not allow the magnetic line to reach the passenger. The speed of this train is almost 603 km per hour, which has made a great world record. So this is how the magnetic levitation train works. The Chinese Maglev train has maximum speed 350 km per hour, but during moving time it's fixed 300 km per hour. But this train create noises also. So nowadays China improved this technology with noise less. China's latest train, the CR450, currently undergoing rigorous testing before it begins commercial service. The train is set to become the fastest operational high-speed train in the world, capable of reaching 400 km per hour during regular service and 450 km per hour during testing. Imagine cutting travel times in half. If this train were in service today, trips that take hours using conventional rail could be completed in a fraction of the time. Berlin to Paris, for example, just 2.5 hours. New York to Washington, D.C., a mere 45 minutes. And Beijing to Shanghai, just 3 hours. Such trains could very well redefine the way people travel, maybe making high-speed rail travel even a competitor to air travel. China unveiled the prototypes in Beijing in December. And according to reports, since then, Chinese engineers have been fine-tuning every detail to ensure maximum performance. And one of the key challenges is weight control. Lighter trains mean greater speeds. But engineers reportedly must balance weight reduction with structural integrity, allowing for precise adjustments to keep the train stable at extreme speeds. And noise is another major challenge. Speed and lightweight materials typically create more noise. But engineers say that they have found ways to minimize sound levels, making for a quieter and more comfortable journey. According to the results of today's tests, the data are excellent. The noise level is far below our limit. I can't disclose the exact figure yet, but it is indeed very good. After 7 years of research, technological advancements and independent innovation, the CR450 is reportedly nearing its final stage of testing in December, bringing the world one step closer to a new era of ultra-fast transportation. If you like a video, please like, share, comment and subscribe our channel for more videos. Thank you for watching.